Hello, everybody. So this this talk. I'm not sure where the idea came from. I know it probably came from the Digital Workflows and Computational Design panel. So if you can think of a better, more catchy title for us, give us some tips on the way out. But the idea of that panel, it sits within the group that sits around the Structures Futures Committee, and we're tasked with thinking about digital workflows and computational design. So by that we mean designing using computers to both help us do the design work, not only structural analysis, but also in a way achieving or doing the concept design. And there is a digital workflow that exists between that and making something, and that's driven generally by machines, which I'll talk about a bit in the lecture, and which are generally, they're called, I'll go through. So the idea is to try and give you, it's almost like a primer, to introduce the idea of digital fabrication, what it is, what it kind of means to structural engineering, I think, because as structural engineers, we have, it's an emerging field, and I think the people who are really pushing the grounds in it at the moment are architects, and we engineers might need to sort of start thinking about catching up. But so I'll give it sort of in two parts really. One is kind of experience that I've had in my career. So we've at Price & Myers have been doing what you might call digital fabrication in various guises for sort of around 20 years, from sort of early projects to now. And then there's some much more exciting work that's been done by other places, generally university departments, especially in Europe, in Germany and Switzerland. So I will show you, but some in the UK too, and at the Bartlett and the AA here. So I'll describe some of their work just so you can see what's going on in the world of digital fabrication. So a few little slides. I asked my colleagues on the Digital Workflows and Computational Design panel to send me through any examples of work they'd done that might be called digital fabrication. And the only person that responded was Stephen Melville, so thank you to Stephen. So, and he has a number of projects. This is University of West England Pavilion, Simple Digital Fab. And he did this thing in, I mean, it's a very broad topic, digital fabrication, and generally I think you would define it as something that's inherently linked to digital design. And this is a broadcast pavilion with Fathom architects, and here they try to get sound waves to be expressed in the cladding, and it can involve quite intricate lattice. Like, I mean, the whole idea of labour and cost of materials and cost of labour is something I'll try and talk about as we go through. But you can see that Stephen especially has done some quite very nice intricate structures here. So this one here, I think we have sort of, one can start to experiment with it, analysing and taking material away. This one's in Portugal. So sort of back to a normal building, and this is I was at a reception for one of my jobs the other night, and we were in this building in the city, and I looked out the window, and it's quite interesting to think about how we build. And we build in a fairly conventional way, and it's a way that's set up to manage risks, and it's a way that's set up to suit a industry that likes to provide us with steel beams and concrete cores, and it's quite systemized as an industry. I mean, an office building is obviously only one part of what we do. And what's sort of what I find interesting about how we make and build the built environment, and there's a lot of what we put up isn't really optimized to be a structure. It's optimized from a fabrication process. So in the case of a steel beam, an I-beam, it actually comes from a rolling mill, and it's an extrusion of the same shape, and it gives you a linear extruded section, which might be fine in a column, but in a beam it means you're wasting quite a lot of material. But these are obviously they're standard parts, and they're what we all pull out to the blue book if we're doing a steel frame building. So what I think digital fabrication, and we design with it, so we have tools. This is Tekla, structural designer, I believe, but tools that allow us to take those parts and build structures out of them, which is fine. And there will always be, I think, that will always be in the world, and there's nothing particularly wrong with it, but it does have an efficiency kind of built in. And as an engineer, I suppose we ought to think, as structural engineers, are we specifiers or are we builders? Or are we makers or are we people who choose stuff out of catalogues and put them together? Because actually, if you think about services engineers, not to criticise service engineers, but they're kind of guardians of the energy use of a building in many ways, and we're the guardians of the energy input when it's constructed, perhaps. And so, if we could think a bit more about how we make things, and this is I was looking for, so I did a talk here on Monday as well, and you basically have to, because we're being filmed, you have to find images that are royalty free where you can provide evidence. So anyway, so I was looking around for forge, because I think the idea of a forge, and the idea of actually shaping material to how you would like it to be, like in the case of an anvil, and optimizing the material in the structure is a really kind of interesting analogy to forging a sword or forging something where you actually shape the metal and you work a finite amount of material and you make it the most efficient it can be. And if you go around Victorian London, you see examples of an era where material was perhaps more scarce and labour was perhaps cheaper, and so what it leads to is a form of structure where things are more optimised for the forces in this case. This is a beam over the canal in Camden, and this is a bridge over the overbridge in Clapham Junction train station. So where this sort of architecture of the windows is sort of bent to the shape of the beam. And I think what digital fabrication might allow us to do is to think, well, actually, we don't have to build everything off a set of standard components. We can actually take material and craft it and shape it in a way using digitally controlled machines. So we're slightly getting away from the labour costs issue, and we can start to build things in a more controlled way that we as engineers can define how things are done. And then issues like Ian's mentioned on Monday, issues of quality on site. If you're actually building it yourself as an engineer, you're defining the process of how everything goes together. And those are other sort of peripheral issues which I think need to be thought about in the context of how we fabricate. So this sort of idea of craftsmanship and thinking about as an engineer, being a custodian of how something might fit together and how something might relate to how all the individual parts are, how you might transfer forces between them, and how you might, get the loads out of, because fundamentally engineering is, we're getting bits of material, whether it's plywood sheets or steel beams, and we're connecting them together so we can transfer loads from one to the other, eventually down into the ground. So this is sort of a traditional craftsmanship. This is a door that was made for Hampton Court Palace recently. And this is one of the projects I'll talk about in a second, which is a section of a sculpture in Heathrow Airport, a Slipstream, it's called, with Richard Wilson as the artist, and Heathrow as the client, and Future City as the curator for it. And this, the team in Price & Myers, because it's not an individual. The other thing to think about is it's real. Everything's a team effort in what we do, but I think in structural engineering combined with digital fabrication, it's sort of even more so. So I'll describe this in a bit, and I'll talk about two projects at either end of the 20 years of digital fabrication experimentation within Price & Myers, and then I'll follow on with the other stuff that's happening in the university departments, as I said at the beginning. Right, so I suppose thinking about what digital fabrication gives you, I was looking for the least digitally fabricated building that I've done, and I think this might be one of them. It's a building in Deal, on the end of Deal Pier, which we designed with Neil McLaughlin, and it's entirely handmade, and it's entirely hand-drawn, and it's a fantastic piece of craftsmanship. and it relies on repetition of parts, which is not necessarily that optimized, but lots of copies of the same thing. So it's a bit like mass production, maybe. Well, in the case that it had lots of these timber frames on their side, and those were repeated, and that's fine. And the the sort of project where we started off doing this sort of work was in 1999 with Neil McLaughlin, and it's a bandstand. It's the Delaware Pavilion in Bexhill, and it has a interesting shaped plywood canopy, which we all slightly scratched our heads in terms of how we would build it, and we came up with the idea of basically stretching a surface between two curves. There's a curve at the front, and a curve at the back, and then at the time I used some software called 3D Studio Max, which is still around, I think, which is more of an organic animation for computer cartoon character type thing, but it's also used for renderings. And together with a joiner in Bath called Michael McHugh, he built this model just to try it out. And the idea, it's a bit like building a boat. There's nothing, if you're a boat builder, this looks all fairly normal. And the way we did it, in terms of building it, we didn't actually have, CNC machines were around in 1999, but I wasn't using them. So what I did is I actually printed all the curves on big long drawings, and then they traced those onto the plywood, and you can see the curves and the grid. So I had a grid on there, and they put the grid on the plywood, and that was then cut out with a bandsaw or jigsaw. So, but I think the point is that I took, as an engineer, kind of responsibility for how the structure of it, how it was, what the shape of it was, what parts were needed to form that shape, how they would fit together, how we would make them, and we ended up with our bandstand, and it's a so effectively it's, even though it didn't involve a computer controlled machine, it did involve quite an intense level of drawing structural components to their exact shape so they could be cut out. We went back recently, and it's slightly suffering. We're trying to get some money together to refurbish it. But Michael bought the old drawings, which was a real treat. So these are the original drawings from 2001 when we eventually did the fabrication. And you can see that lots of stuff. It's like a warming feeling seeing that. Right, girls, Alex, can you bring a glass of water down? Thanks. So I've got my daughters at the back and their support crew. Right. So moving forwards in life. This is so fundamentally, I think with digital fabrication, you need some digital information, and you need a digitally controlled machine. So the simplest piece of digital information is a sort of 2D profile drawing, DXF or DWG, and that would drive something like this. So this is a 3-axis CNC controlled router. So CNC stands for computing numerically controlled, and it goes with a computer, and it goes with a piece of software that's called CAM software, computer-aided manufacture software, and you have your profile of a piece of, in this case, a slice of plywood, and you then process that, and the software works out how the tool moves around so that it can cut out that shape. So that's almost like a pen plotter, an old-fashioned pen plotter, the same technique. So this is called a toolpath generator, and you can control depth of cut and how fast it goes. And fundamentally, all digital fabrication is doing is it's taking a tool that you might manipulate by hand, and it manipulates it with a machine that moves it around and interacts with a piece of material. So it's a very, and then sort of the basic premise is very simple, really. And a lot of this sort of going from a drawing to a machine that's moving through a piece of plywood, cutting your thing out. Thank you, Alex. Great. Cheers. So a lot of this stuff is actually automated, so there's software that does it, and especially now, there's lots of companies. It's an extremely competitive market, so there's no reason you don't need to buy one of these machines. You can there's a multitude of suppliers who will cut this stuff for you. You send them the drawings, they will send you back the bits in a box. So it's not a excuse me. It's basically what I'm trying to say. It's something we can all do because we all draw with CAD and we can all work out how things might fit together. And I will now explain a more detailed project, which is Slipstream. So this is the sculpture in Heathrow. This is one of Richard Wilson, one of his paintings of the initial idea. And the idea in a nutshell is what would happen. Oop. Is that going to play? Press it. Yeah. So what would happen if you could solidify the shape of a moving stunt plane through the space? So this is the car park of Heathrow Terminal 2, and behind you is the terminal, and a big covered courtyard, open at each end. And the idea was to try and manifest that idea into a shape. So this involved big team in Price & Myers involving an architect, some structural engineers, and a fabrication team up in Hull called CSI. And we entered the competition together and built this. This is the back end of it. So I'll just talk through kind of how that was different from a fabrication, well, how the digital fabrication process affected our work as structural engineers in building it. And the first thing was that we took on responsibility to produce all the information, which seemed like so rather than just doing structural engineering, we did we defined every single part in this sculpture, and we chose to build it using timber around a steel frame. So it has a steel armature that runs through the middle, and we went through a process of defining that shape, and that was done with an in-house architect called Ralph Parker, who was in our team. He's in our team, and that kind of responsibility is quite concentrated and it means that the actual time you spend as a consultant digitally fabricating something and digitally designing something is orders of magnitude greater than if you're just doing a more basic structural engineering service. So it involved working out what that shape was, working out how to tweak the shape to fit a structure that would span between the columns in Heathrow Terminal 2, and then really inventing a building system that with the fabricators that we could all sign up to and we could all make work, because because of the way the sculpture's conceived, there's no part that's the same. So it's roughly 35,000 different shaped parts. So what we start with is a frame, and this is this is the thing on its side. So imagine the sort of axis of the sculpture tipped 90 degrees. So this central rib, this central box section, 400 box section, flows through the central line of the sculpture, and then has these outriggers that basically fit where the wings and the tail fin of the plane sort of define the shape. And then this is digitally fabricated because each of these is different, and these are all cut with laser cut tube profilers. So you can send tubes to be profiled on a laser cutter, which will go around the section. And the advantage of that is it will read a 3D file, so you don't need to produce hundreds of drawings. Because imagine if we had to do 35,000 A1 drawings. So we needed to find a way that we could automate giving people information just because of the vastness of the job, and also automate a way that we could get the computer to produce that information. So there were various components. So these are bulkheads that define the shape, and these are all designed to be made on a computer-controlled router that, like I showed just recently. just now, and that has sort of dovetail joints so you can notch stuff together, and it's designed so it can fit around the tubes and the various parts of that steel frame. So you're really, getting fully involved in how something is built down to the sort of finest level of detail. It then has strips of plywood that define the corners, and then more strips of plywood. These are all planar, so these can all be cut from flat sheets of plywood, and these notch into the bulkheads. That gives you your load path and your ability to make a robust structure. Then you clad that in plywood to give you a stress skin on the outside, and finally it has the aluminium skin, which is the sort of the artistic surface of the piece. So that process of designing it and then building it. So this is one of those parts on its end. It's about 3.8 meters high. Then you basically have to start interfacing with the machine. So this is a CNC router, not the one I showed before, but one that is owned by the contractor. And you immediately, one of the interesting things that happened on the project was that our drawings initially didn't work on this router all the time. So we would find it would have little squiggles of line where we'd intersected surfaces and to create profiles. And those would cause the machine to go around in circles and set itself on fire. So, and we of course got blamed for that, so completely our fault. Maybe not, but anyway. So that was, so these unexpected things that you have to sit and you have to work with people. Think, how can we never come across this problem before? But and it basically involved reprogramming the machine and sort of editing out bugs. So you find things that you wouldn't normally expect because you're trying something new. But you get to a stage where you can produce a 3D model, and then you can produce the real thing, and they're exact copies. And it's actually quite unsurprising when you go and see it in the factory, because it just looks like what's been spun around on the computer screen all day. And in a sort of strange way, the factory kind of is the office. So this is at the height of producing all that information. So that's Ralph, who's in charge of it all, really, on the architecture side, and Emmanuel, who did most of the engineering with Rob, and then two drafts from John, Tass and James. And there was that's Will, sorry. 5 people on CATIA, which is a 3D modelling program, working as if they're producing information. So it sort of, I think what we learned from this project is it doesn't necessarily work if you have to do it in a central London office with central London overheads, but never mind, we did get there. And each part is different. You have the ability to have a fantastic amount of coordination. So these screw holes were pre-drilled so that the people drilling them on, so they would lie over a bulkhead that's behind. So you can sort of build in this sort of craftsmanship quality into the design, and really so you can aid hand assembly. And some of the stuff I'll show later is more automated assembly. So this was digitally created parts which were then hand assembled, but in such a way that the thing jigged itself. And it had enough accuracy and coordination in it to make it fit together and make it so you didn't need hundreds of drawings. So the drawings were one drawing that defined the dimensions of these central steel frames, and those are themselves defined on 3 points, and then everything else more or less fitted together like a 3D, like those plywood dinosaur type jigsaw puzzles. Then that came together on site, and this is you end up shipping very large, unusually shaped bits of thing around the country in the middle of the night, and fitted together, and so the back end of it's fairly conventional, I guess, but it does rely on, certainly here, on something that's pre-manufactured and really trying to build the biggest thing you can possibly transport. So logistics, how you can fit things on the back of a lorry, how you can fit under low bridges, all of that stuff comes into the fore. And then, since you've got all those drawings, you can build your own model. So that's a model we have in the office in the reception of P&M. And more recently, we've done this, and we've thought about how can you do this to sort of save metal and save materials. This is an advertising screen that we're working on that's going up at the moment. I'll flick through this because it's really the same idea, but manifested in steel. So it's with Wildstone, who are an advertising company, outdoor advertising company, and it has a stalk and then these fingers sort of like that, and they hold an advertising screen. And each of those fingers is designed so the surfaces weld together and form a structural triangular section. One of those is planar, so it can sit on the floor of the workshop, and we can actually set the thing out easily. And then these two outer ones curve together, and then it has bulkhead. So that is all made possible by a technology that's been in fabricators' shops for years, which is CNC-controlled plasma cutters. And they cut the steel sheet. You end up with lots of different shaped, banana-shaped pieces of steel that all have to have the right number on, otherwise it's complete confusion. But this ability to create a very accurate thing that you know will fit together. So you as an engineer, our attitude at work is that we know that it'll fit together, so we can effectively do the fabrication drawings for the contractor. These are the fingers which go together, and it's going up at the moment. So so really, spot this man in the audience. This is Julio and my team, and just want to sort of describe, because without the digital design process, there's no digital fabrication, and you really can't take advantage of it, because the design process allows us to optimize, and it allows us to use computer power to go through cycles and try different things out. And I think Tom Webster, who's also on the digital structures panel, has done a talk about awareness of scripting. So what we have here is GSA, Oasis GSA, and then Rhino and Grasshopper. So GSA, you probably all heard of, is finite element modeling tool. Rhino is 3D modeling software, and then Grasshopper is a visual scripting language. So sorry if this is sounding like teaching people to suck eggs, but just so people, everyone can see what we're doing. And the core thing is that these boxes just describe instructions. This is what's called a Grasshopper definition, and Julio explained it to me this morning. But this bit, basically, each bit does different parts within the 3D model. So this bit over here, in this case, defines the shape of the overall form, right down to this part draws a GSA mesh so that it can be flipped backwards and forwards between the modelling software and the analysis software. That's a different. I mean, they're quite amazingly beautiful things, actually. And you can see a sort of common purpose of all these lines coming with some form of output. And what that gives you is it gives you something that you can put in the software, analyze it, try a different option. There's no real time penalty. So this going backwards and forwards. This is the model. That's basically a mesh of the legs of this thing, and that process then, gives you something that is minimal potentially, hopefully, and can then go off into the world to be made. And that making really, I mean, most of the interesting stuff that's happening in the world relies on robots. And that's sort of that a robot, especially kind of taking jobs, and the whole way that robots will revolutionise things in the future. That's sort of in discussion a lot at the moment. Is often seen as a threat, but I think in engineering and architecture, it's actually a huge opportunity where we can really start to build stuff that we couldn't have done before. So this one might be a threat. This is a burger flipping robot that flips over burgers. So that might take someone's job. But this is a architecture robot. So this is a former industrial. It's an industrial robot with various axes, big robot arm basically that you would see in a car plant. And in this case, this is ETH in Switzerland, and they put it on a base with tracks so it can move around. And the tasks that these things can do are sort of more or less is limited by your imagination. So the key thing that we're looking at is a robot arm that's somewhere. So is that fixed or does that move around? And then it has something on the end, and that end bit's called an end effector with an E. and that's either a drill or a saw, or in this case it's a sucker that grabs these timber blocks. So I'm just going to show you some of the stuff that's going on at the moment. And these pavilions aren't massive. I mean, some of them are sort of 5 years old, but or older. But I think they show us the future of what could be done. And I'm very grateful for these organisations for allowing us to use the images. So Bartlett, the AA School of Architecture here in London, Grammatica Koller Research at ETH in Zurich, and ICD and the University of Stuttgart, Achim Menges' team. So I'll start with ICD's work. So this is me really just being a reporter. So I haven't been involved in any of these projects. I'm just looking at them as an observer and of someone who has done a fair amount of digital fabrication work and can see, as an engineer, kind of what the future might, what the potential for some of these projects is. So every year ICD in Stuttgart produces a pavilion, and this was the one from 2011, and you can see the sort of scale of it. And I think that every year they sort of look through nature, where they look at nature and they find various organisms and things that interest them. So in this case, this shell, which has a way of knitting together its shell, and then they basically then produce a fabricated version that has some of those qualities and uses the tool. So these are their slides. But the key thing is they're thinking about how you might manipulate that material and how you might control the path of a tool to cut that material and shape it. So these are called tool paths. So what happens on this slide back here, basically that you process your geometry and through various bits of software that you write, and it gives you G-code, which is basically instructions for how the machine should move and how it should cut the material. So in this case, the end effector is simply a router bit that's on a spindle. So that's very similar to the 3-axis CNC router that I showed earlier, but it's attached to a robot arm. So this is the end effector. This is the spindle that spins the tool. This is the robot arm, which can rotate in 6 axes, and then you have another tool here that can also rotate. So the tool here can rotate the piece and you can tilt it, and the robot arm can move. So between them, they can pretty much get to any position and cut the wood. So this is these dovetail joints for the panels of plywood, and what you have is a huge level of precision and coordination that allows all these joints to be perfectly machined and to fit together. I'm making it sound very easy. I'm sure it's pretty complicated. And so on this pavilion, what's very interesting is that you get this very good structural connection between 2 sheets of plywood that effectively, does that goal of joining material together. So you have a very long glue line. You have you don't have to rely on, say, mechanical bolts and screws to get things out. So that looks like that. And then that's been recently they did this other pavilion. This is a exhibition hall and relies on slightly thicker wood. This is beech laminated veneered lumber, about 50 mil thick, and they've gone through a similar process of basically dovetailing the stuff together and then using that thickness to produce screw holes. But you can see here, this just would not be possible to get that screw at that angle, each one being different in the whole thing. So this idea of customization of the part doesn't actually need to cost anything in the production process, because you're sort of designing at the very beginning, at the very outset, in a more strategic way, that you are incorporating how you're going to build it into how the structure works and what the material choice is. So in this case, there are blanks, so they do a rough cut of each part, and then it goes on goes back on the robot and it produces this work. It's actually contained in this glass enclosure, because the robots could, they're quite heavy things and they can move quite fast. And they produce a huge amount of dust as well. So I think that just keeps the dust down. You see how it's covered. But this end effector now is a drill that's doing that screw hole. So the opportunities really are there. I mean, this is robots doing stuff with panelized wood, which is only one aspect of sort of current research. But so that's the interior, which is structural, and then it's clad with insulation and membranes before being put on top. And it's actually very simple. What's quite nice is that the actual formwork is very minimal. And it's really, I guess, there just to help define the shape, and then the thing, I'm sure, holds together and arches up, actually arches up from the ground. So you have this amazing thing where this thing that looks like it's been put in by highly skilled joiners has been built by a team of highly skilled architects and engineers and robot technicians working together to actually control how a machine moves around a piece of wood. This project is by the AA's Design and Make unit in Hook Park. So the AA Architectural Association has a woodland campus down in Dorset called Hook Park. And it's called the Wood Chip Barn. I mean, all these projects, you should look them up online because there's really interesting videos. Lots of these have a Vimeo attached to them. And the idea here is to use tree forks, so beech trees, and to take advantage of this fork that you get in a tree between two big branches and work out how those could be made into a structure. Now, the thing is, department of the blindingly obvious, that you might not necessarily know what shape that was unless you scanned it. So the ability to be able to 3D scan something, whether it's a piece of wood or the environment you're installing a structure into or a structure itself, gives you that, as a sort of digital fabricator, the ability to then start manipulating that, because you're not, say, relying on my steel beam is this height and this width of flange and all that stuff. You have to actually discover what things are. So this is a 3D scan of one of those pieces of wood, which they then went through a process of optimizing the position of each one, again through process scripting, computer programming, to actually come up with an arrangement that fitted together. And then once they did that, this is the arrangement as a rendering, where they can notch and dowel and mortise and tenon all these parts together into a sort of structural arch. The robot can then know where something is and then can then start manipulating it and cutting it and drilling it and milling it. This is a chainsaw end effector. So really, anything that you could, any tool that you could do anything with. You could have a hammer end effector, I suppose. I mean, it could be. It's really. It's so simple. The idea is you control the movement of a tool through computer programming. So that's that piece of work. Really, really fantastic. Additive manufacturing, 3D printing. Okay, so there's a few projects around which are interpreting this in, I think, really interesting ways. So. This is an ETH piece, I believe, that was in the Venice Biennale last year, and it's a 3D print of sand. So this is a technology that's come from sand casting, where you can 3D print sand in a mold, and then that can then be used to cast metal. And in the case of this demonstration piece, it's got small enough. It's small enough that that sand with the binder that holds it together can work as a structure, and they can start experimenting with deleting out the low stress areas. But again, ETH with Komatsu Kola Research been doing some very interesting work in taking robot arms and actually using them on site. So this is a demonstration project where they put a robot in a shipping container. So the robot is obviously here. That's where the end effector would go. And the various arms, but it also has a track that can move up and down. So the thing is able to move around, and then it was transported, caged up in its box like that, with the brick lifting end effector on. taken to the Giardini in Venice and used to build these brick walls, which eventually went together into the Swiss Pavilion, which looks like a fairly arty project, but then you should realise that this is made in the same way, and that could be really, that could be a facade on a building, a module of a building that's made with a robot. So the technology is there to move and manipulate standard parts, and the idea of the additive manufacturing, where you're only putting material exactly where you need it, could be really reinterpreted by being able to build brick structures where you literally built the brickwork where you wanted it and not elsewhere. This is their work as well, flying drones. I think these are made. I don't think these are made of clay. I think they're made of foam. But this is in Frac, which is in Orléans in France. But a large-scale object that's been basically made by drones lifting pieces and dropping them into position. So the drones were camped out on these pods, and then they basically lifted and dropped stuff into place. Can anyone guess what this is making? So this is again the same team, Komatsu Kola. This is gravel, coarse aggregate, probably 20 to 50 mil, and this is an end effector that extrudes string. So the string comes in here, goes over this wheel and is pushed out and then loops around. And then what they do is they build up layer after layer of gravel in this formwork, here with a robot arm on a very tall channel so that it can move up. And then when they there's a brilliant video, you should look online for this. And then basically they start off with this big tall monolith, and they chip away at it, and everything that's not bound in by a string falls away, and you have the shape that's left. So I think it's really fascinating in terms of just what one can think of in terms of how you can place material and how you can think about where that material might go to make it useful in a structure to carry load or to do something else. Back on the idea of the forge, this is Arup's work with the University of Sheffield of 3D printing nodes. So this is a node. This is the same node where they've done a process called topological optimization. So if I've got that right, where you basically take away, you analyze it, and you actually remove bits of geometry that don't carry much load. And what you end up with is a very, very, it's almost scary how little material there is, but it really sort of pushes home the point that most material comes from the manufacturing process, not actually the needs of the structure. So this is really fascinating piece of work. And then the additive bit needn't be powdered metal, or it needn't be stones or clay or extruded plastic. This roof structure, again at ETH, is basically using small spars of wood, small planks of wood, which are basically assembled in a sort of additive manufacturing type of way, using a robot that places the timber parts and then screws them together to produce this form of structure. So I say I'm just a reporter on these, but they do sort of give us an idea of what might be achieved. And then finally, this is the back at ICD in Stuttgart, and they've been experimenting, and there was a pavilion in the B&A last summer, which might still be there, where they're looking at winding filaments and using glass fibre and carbon fibre strands, and those basically are woven onto a piece, knitted onto a piece almost, with resin that fuses them together. So you get this kind of result. So makes us think, and this is a more recent thing. But if you do think about this is again back on my opening do the other night in the city, and this is higher up that slide I showed at the beginning. But a core of a building is a bit like a 3D printing machine, isn't it? But we don't actually take advantage of deleting any of the redundant material that that's in there. So that might be something to think about in terms of how we could at least build concrete cores or bridge piers in the future. I think obviously education is going to be hugely important in terms of helping. I mean, what I've noticed in my 20 years or so of working already is that people who come out of universities now are tooled up with knowledge of scripting, and they think much more about how things go together than they might have done in the past. I also work at UCL in the Bartlett School of Architecture, and we're starting a course this September called Design for Manufacture, which is going to really research and teach these areas. It's going to be based here east, out in the Olympic Park. I don't have any pictures of the interior, but this is the publicity shots of how it might look. So we have a factory scale space, and what we've done in the past in the Bartlett is started to build some interesting life-size projects. So rather than students building architectural models, this is Unit 17 last year, where the Year 4 students built this full-scale version of a chapel where they deleted the stones and the mortar joints with the structure. So it's just built in fibre reinforced concrete, but with robotic carving of all the bits of polystyrene that go together. So these things do happen, and we need to sort of be on board with it. This is a nice quote from a futurologist called Clay Shirky. Communication tools don't get socially interesting until they get technologically boring, and the sort of thought that we need to actually make that technology a lot more easy to use and a lot more boring. This is a home project that I'm going to embarrass my kids now who are here at the back. But our last half term, we had World Book Day. Oops, sorry, go forward, I'm spoiling the surprise. And the idea was to do an Ezio Trot outfit. Ezio Trot is if you know Roald Dahl, lots of different shaped tortoises. And we were able, through fairly basic technology, so to 3D scan, this is Rosalind, my older daughter. So if you photograph someone from lots of different points of view, and then you put it through some software, it will produce a 3D model of that object, which is amazing. And that software is more or less free, and it involves vast amounts of computing power, but that's all done in the cloud on servers. And then we designed this fairly simple shell based on planar pentagons and hexagons that could fit together to look roughly like a tortoise shell. We have a laser cutter at work, so we cut all these bits out in plywood, and sort of huge jigsaw puzzle, but I didn't put any numbers on, so it was even more confusing. And it all came together, sort of home project. So, I mean, that's something that I do for fun in my spare time, but you sort of hope that if we can make things an order of magnitude simpler and easier, and people get more skilled, then they might, we might actually find it easier as engineers and design teams and professionals to sort of make advantage of to take advantage of these tools, because the stuff is there, the technology is there, the tools are there, the software is there, the people coming out of universities who know how to use the software are there. We just need to put it all together and start doing stuff. So I'm going to end on that. I'm going to say thank you again to these guys for letting us use their projects as examples, and thank you very much.